Good day, everyone. I am Joel Ishali Jr., your teacher at the moment, and welcome to my lecture video. Our topic for today is the Module 6, the logic statement. So, are you ready? Because at the end of the lesson, you are expected to differentiate English language and mathematical languages, and explain logical connectives and construct truth tables. So in this lesson, we'll introduce you a mathematical way of thinking that can serve you in a wide variety of situations. The lesson aims to give you some ideas about the characteristics and conventions of mathematics as a language that is a foundation for dealing with everyday life. It also focuses on logical symbols, logical connectives, truth tables, and tautologies. You should listen carefully so that you'll understand it clearly. As I've said earlier, the students are expected to differentiate English language to mathematical languages and explain logical connectives and construct truth tables. Our lesson 1 is the mathematical expressions, sentences, and statements. So mathematical expression, it is the mathematical analog of an English noun, and it does not state a complete thought. Unlike to mathematical sentences, it is the analog of an English sentence and state a complete thought, and it makes sense to ask about the truth of the sentence if it is true or false. It is sometimes true or false. Unlike the mathematical statement, it is a declarative sentence that is either true or false, but not both true and false. So the statement is classified into two, the simple statement and the compound statement. A simple statement, it conveys a single idea, and a compound statement, it conveys two or more ideas. Mathematical symbols, the truth value of a simple statement is either true or false. The truth value of a compound statement depends on the truth values of its simple statements and its connectives. A truth table is a table that shows the truth value of a compound statement for all possible truth values of its simple statements. So let's have an example. 7 is less than to 10. Is it a statement or not? It is a statement. So can you determine if it is true or false? 7 less than to 10, true or false? It is true. Second example, a cat is a fish. It is a statement or not? It is a statement, because it has a complete thought that we can identify. And if you observing the concept, is it true or false? It is false, because a cat is not a fish. A cat is an animal. Okay, so third example, 2 plus 3 is equal to 5. It is a statement or not? It is a statement. And can you determine whether it is true or false? It is true. Now let's move to the logical connectives. If two or more statements are joined or connected, then we can form compound statements. These compound statements are joined by logical connectives and, or, if then, and if and only if. So let me give you an example. So your first statement is John ate fries, and second statement is Mario drinks soda. So what you are going to do is to use these logical connectives, the and, or, if then, and if and only if. So let's look at the table. Table 1, the symbolic form of compound statements with P and Q as the simple statement. So your first statement is P and the second statement is Q. So it is important to remember their their statement symbolic form determining using the type of statement. So, the symbolic form of negation is not P, or we have assigned that assign. Then, sa statement not P, and sa conjunction is P and Q, and sa disjunction is P or Q, sa conditional if P then Q, and sa biconditional P if and only if Q. So what are the connective of the statement? So the connective for negation is not, in conjunction, and in disjunction, or in conditional if then, and last sa biconditional if and only if. Their symbolic form is shown in the table, and the statements are represented symbolically by lowercase letters P, Q, R, and S, and the new statement can be created from existing statements in many ways. So we have the first type of statement, the negation. So in negation, if P represents the statement, then the negation of P written as negation P and read not P. When a statement is true, its negation is false, and when a statement is false, its negation is true. That is, a statement and its negation have opposite truth values. This relationship between a statement and its negation is summarized in table of negation. So let's have an example. Rick is here. So what would be the possible negation of your first statement? So Rick is not here, because not is the connective of your negation, of your type of statement, which is the negation. So the second statement type of statement is conjunction. If P is your first statement and Q is the second statement, and their symbol is P, or can be read as P and Q. The conjunction of two statements P and Q is true when both P and Q are true. So the table is shown in the conjunction. So let's have an example. So John eats fries is your first statement, and Maria drinks soda is your second statement. So when you're converting the following conjunctive proposition in two words, so it can be the result or the solution is John eats fries and Maria drinks soda. The and is your connective in conjunctions, in that type of conjunctions. So the third type of statement is the disjunction. So the disjunction of statement P and Q is the statement. It can be read as P or Q, denoted by P or Q, and is defined through its truth table in table shown in the truth table of disjunction. So a disjunction sentence is false only if its constituents or the disjuncts are both false. So let's have an example. So John eats fries is your first statement, and Maria drinks soda is your second statement. So in translating the following disjunctive preposition into words, or in combining the two statements, it can be read as John eats fries or Maria drinks soda. So in solving the type of statement, we have a given, which is the P and Q. P is your first statement and Q is your second statement. And in P, there are given a statement which is the true, true, false, and false. And for the second statement, which is the Q, has its given, which is the true, false, true, and false. And that would never change. because that is your basis when solving the problem. Our next type of statement, the conditional. So the statement if P and if P then Q, denoted by P arrowed by Q. So read as if P then implies Q is called an implication or conditional statement. P is called the hypothesis and Q is called the conclusion. So the truth table of a conditional statement can either be true or false. In order to show that conditional is true, just show that every time the hypothesis is true, the conclusion is also true. Also, if both the premise and conclusion are false, the conditional statement is true. To show that a conditional is false, you just need to show that every time the hypothesis is true, the conclusion is false. If you can't find just one single example such that the hypothesis is true, but the conclusion is false, then the conditional is false. So the example of conditional statement. So your first statement is John eat fries, and your second statement is Maria drinks soda. So in translating the following conditional proposition into words, we have if John eats fries, then Maria drinks soda. The if then is your connected verb found in the conditional statement. And now let's move to our last type of statement, which is the biconditional. Notice that the biconditional P and Q is true when P and Q have the same truth values and false otherwise. Often in mathematics, the words necessary and sufficient are used to describe conditionals and biconditionals. So let's have an example. Your first statement is John ate fries, and your second statement is Maria drinks soda. So when combining these two statements using the biconditional or their connected, which is the if and only if, so the result will be John eat fries if and only if Maria drinks soda. So now let's go to our last discussion, which is the tautologies and self-contradiction. So a tautology is a statement that is always true. Second is the self-contradiction. It's a statement that is always false. And last is the contingency, if the last column has true and false. So let me give you an illustration. So let's solve the given problem. So the given is negation P and Q. So to solve this, we have a given statement, which is the P and Q. The P is always never change the statement that true, true, false, and false. And for the Q, the true, false, true, and false. So your next column to solve is the negation P, which is the inverse of the P. So if the given statement in the original P is true, true, false, and false, and the negation is false, false, true, and true. The next column to solve is the negation Q, which is the same process of how we get the negation P. So our last to solve is the whole given problem, the negation P and the negation Q. So the connective of the last column is the and, which is the type of statement is conjunction. So if we look for the negation P and negation Q found in the column, in the third and fourth column, in the first line, the false and false, and the result will be false in conjunction. So in the second line, if false, true, so the result will be false. So in third lines, true and false, the result will be false. And last line is true and true, so the result will be true. If we look to the result of the last column, the negation P and negation Q, so we can determine that it is contingency, both true and false. That can be seen in the last column of your solution. That would be all, everyone, and I hope you gain some knowledge or understanding about the logic statement. So once again, I am your teacher at the moment, Joel Sally Jr., and thank you for listening.